Okay, so today's class is measures of dispersion, and the topics that we'll be covering are the range, population variance, population standard deviation, sample variance, and the sample standard deviation. Okay, what we're looking at in terms of data dispersion, and by definition, to what degree is your data distributed across the units of your scale? So variability provides a quantitative measure of the degree to which scores in a distribution are spread out or clustered together. The three measures that we use are the range, the variance, and the standard deviation. The first one is the range. It's the crudest measure of dispersion. And it's really your highest score minus your lowest score. It's not the best measure, but it does give you a quick eyeball of indicator of just the overall dispersion, max and min. We do take into consideration, if we're technically going to do this correctly, the upper real limit for x max and the lower real limit for x min. So as we can see here, this data set, you can see right up here. So right here, I have the data sorted by subject, and it's what I want to do is I want to sort by grade. So I want it from the lowest grade to I've done this one, highest grade to the lowest grade. So once I do my sort, I can see that the highest grade is 82 and the lowest grade is 45. Okay. So now if we're looking at 82, the real limits for 82 are 82.5 and 80. I'm going to screw this one up. 81.5. So 82 extends from 81.5 to 82.5. This is the lower real limit. This is the upper real limit. And the one I want is the upper real limit, the 82.5. That's actually a 2. Okay. Now the lowest score is 45. And the limits for 45 are for 45.5, and the lower real limit is 44.5. So this is the lower real limit, and this is the upper real limit. So the lower real limit is what I want, so it's the 44.5. So I just do the math. 82.5 minus 44.5 is 38. And this is just ignore that. So that's the range. Now, you could just have easily have taken 82 minus 45. And that's, because it is such a crude measure, we typically just go with the raw upper score minus the raw lower score. But technically, you should be using the real limits. What's going on here? There we go. Okay. I have this small group of aliens. This is just a little practice one. So 65.5 minus 34.5, range of 31. So what I have is, so 4 small aliens land in my backyard. They're little short things. They are the last remaining members of their species. So this is important because they actually represent the population. They're the only 4 remaining aliens of that population. That's going to be important in a sec. But this is just a practice for the calculating the range. So you give it a shot. Obviously 65.5 is the upper real limit, and for 65, and the lower real limit for 35 is 34.5, giving me a range of 31. Okay. The preferred measure is the variance. The variance complements the measures of central tendency in the mean. So what we're looking at is the deviation of each score from the mean. So how much does each score deviate from the mean? Now we're going to see a problem with this because, as we saw last week, the mean is kind of like a balancing point. So it has kind of like some weird physical property that if you were to put all the values on an imaginary line that's weightless, and each value is of equal weighting, then the mean will balance that line that has all those weights on it across the units of measure, right? Okay. Okay, so let's just get right to the calculation. So what I have is I have my aliens here, and why is that not doing what I want it to do? Let's clear it. Okay, so the balance point. So if I look at the values, so I got my 45, 35, 55, and I have my 65. And my mean, the balance point, is, I'll put it down here, 50. Okay, so this value here, that's minus 5. This value here is minus 10 from the mean. On the other side of this, 55 is plus 5 from the mean, and 65 is plus 10. Now the 50 serves as that balance point. So on the negative side, if I sum them up, it sums up to minus 15. And on the positive side, it sums up to plus 15. And that will always be the case where the sum of the negatives equals the sum of the positives in terms of absolute values. So minus 15 plus 15 equals 0. So because of the property of the mean, the sum of the deviations from the mean, right, x minus the mean is how far does each value deviate from the mean. This value will always add up to 0. So that'll always be a 0, no matter what. So I really can't use this as a measure of dispersion to see how far each score deviates from the mean, because it will always add up to 0. One solution would be to take it as an absolute value and just strip off the minus signs, but mathematically that's not very efficient. The most efficient solution is to square the values. So if I square the values, that gets rid of the minus sign. So what I do is I take 65 minus 50, the mean is 50. If I take that, the value is 15, square it to 25. 55 minus 50 is 5, square that, it's 25. Now here it is, 45 minus 50 is actually minus 5. Well, minus 5 squared is minus 5 times by minus 5, which is 25. Multiplying two minuses makes a positive. Similarly, minus 15 times by minus 15 is equal to 225. In this case, by squaring the values, it doesn't sum up to 0 anymore, which is what I need. I need it to be some value other than 0. Now, it costs me a little bit because my unit of measure has changed. When I take, let's say, let me get my thing back. Let me clear. So if I take, let's say, 5 grams, and that's this one right here, and I multiply it by 5 grams, I'm squaring it, that's going to be 25 grams squared. So my unit of measure goes from grams to grams squared. So there's a cost here because I now have, it's weird, I now have a different funky unit of measure. Okay, so I sum those up. It sums up to 500 grams squared. I divide it by n. So what is the average of these squared deviations. So what I'm looking at is I get the average of these values here. So what's the average? So what is the average of these values here? Well, the average is basically the sum of some value divided by n. Well, what am I summing up? Well, in here, I'm putting in the x minus mu squared. Right, so that's what's going in there. So I'm calculating what is the average of the squared deviations from the mean. So the AVE of the squared deviations from the mean. Okay, so 500 divided by 4. The average of the squared deviations from the mean is 125 grams squared, and that's my variance, and that's my indicator of dispersion. On average, the values, the squared differences from the mean across my 4 aliens is 125 grams. Oopsie. Now, what I need to do is my unit for my my variance is 125 grams squared. So as a descriptive statistic, what I want to do is I want that to be in my original unit of measure, grams. So if my unit of measure is grams, so my unit of measure is grams squared. If I take the square root of that, my unit of measure now becomes just grams. So to convert it back to its original unit of measure, I take the square root of the variance, which is the 125, and my descriptive stat for dispersion, and back in my original units of measure, is 11.18 grams. And that is the population standard deviation. Sorry for my snottiness. Okay. Now, this was great when I had my population. So here's my population. And when I'm dealing with a population, which is everybody, I'm dealing in Greek letters like sigma, mu, and the N for a population is the capital letter N. So the capital letter N refers to the total number of people in the population. When I don't have the whole population, and I take a subset of that population, which is referred to as a sample. So if I randomly draw a sample, I want to use that sample to estimate, and use the data from that sample to estimate the population standard deviation. Right? I want to, like, if I have my sample, I want my sample to say, okay, here's my sample standard deviation. It's an unbiased estimator of the true population standard deviation. If it wasn't, there'd be no point in even calculating it because it would just be something wacky. What happens is if I calculate the sample standard deviation and I just use this formula here, believe it or not, that's an arrow. Not good. Here's an arrow. Get a little better. If I use this formula here, what will happen is my sample standard deviation will be a biased estimate of the population standard deviation. And what it'll be is, on average, it'll be smaller. My sample standard deviation calculated plugging in this formula will be on average smaller than my true population standard deviation. So to make my sample standard deviation an unbiased estimate of the true population standard deviation, I divide by n minus 1. And the n minus 1 is a correction for the inherent bias. Okay. Okay, so we draw a population of Finlanders, and there's a sample of Finlanders. My formula changes, and we'll walk through that calculation. So, sample standard deviation calculation. I don't have access to the whole population of leopard geckos, but I want an estimate of the population standard deviation for the weight of all geckos. To estimate the standard deviation for the weight of geckos, I draw a random sample from the population. So my random sample has 3 geckos in it. And my 3 geckos, for gecko 1 weighs 4 grams, gecko 2 weighs 6 grams, and gecko 3 weighs 8 grams. And now we're just going to walk through the calculations again. Okay. So, what do? I calculate the deviation from the mean. And what will it always, if I don't square it, what will it always add up to? 0. So what do I have to do to make sure it doesn't always add up to 0? I square the values. So I square the deviations from the mean. So minus 2 times minus 2 is 4. 0 times by 0 is 0. And 2 times by 2 is 4. The mean in this case was 6 grams. And then I calculate the sum of the squared deviations from the mean. And you'll see now through this semester and next that the sum of the squared deviations is abbreviated to sum of squares, and then further abbreviated to the acronym SS. So sum of squares, you'll see SS in text. That refers to the sum of squares, and what that means is you're taking the sum of the squared deviations from the mean. Now, it doesn't add up to 0. So 4 plus 0 plus 4 equals 8. I take that sum of squares for the sample variance, and I divide it by n minus 1. And as you can see in the formula, so in the formula down here, so here's the 8. I divide by n minus 1, which is 3 minus 1 is 2. 8 divided by 2 equals 4. So my sample variance is 4 grams squared. Now, as you can see, when I'm in the sample variance, I use the alphabet letters. So S squared for the variance, M for the mean, and little n for the size of my sample. Once again, when I calculate the variance of 4, that's 4 grams squared. To get it into the original unit of measure, I take 4, and that's the square root of, so 4 to the power, 4 squared. Oh, what the hell's this? Oh, it's right here. So this would be the square root of 4. Equals 2. So, but it's actually the square root of 4 grams squared equals 2 grams. So my sample standard deviation is 2 grams. One final thing that you're going to see is what's referred to as definitional versus computational formulae. Up in the top right-hand corner is the calculation using the computational formula. The computational formula was something that you would have done if you didn't have a hand calculator, or if you had a hand calculator even before, if you had to do things by hand, if you were actually a human computer. And there were people who were actually computers. They would do a lot of the processing, in a sense, in terms of iterative, repetitive calculations. And sometimes it would be very complex. So that formula you see as a computational, there's not any rounding. It's easier to sum up, and it gives you the same result. But since we do things in Excel and SPSS and on computers, we then just don't have to really worry about computational formula. We can just use the definitional formula. Okay, so definitional formula, it's easier to define, easier to understand. Cons, there's some rounding errors you got to sometimes deal with, and it's just a little trickier in terms of calculation. It's a little, in terms of it is a little trickier calculation. Whereas the computational formula, you're just summing up squared values and summing up taking the total sum and squaring it. It's easy to calculate, reduces rounding errors. but it's kind of like doesn't really tell you what's going on. So I always stick with the definitional formula. And for those interested, this is just for the fun of it. You can completely ignore this slide. This is what the proof from going from so this is the proof from going from what we do. My little pen's not working. So this is what we used, and this loops you around step by step in terms of just working the math proof to get down to the computational formula, which this gives you the same value with this in terms of hand calculations. The computational is probably the better one, but if you're doing it in SPSS or Excel, just keep it with the definitional. And that's it. Sorry for my allergy issues. So, allergy issues.